Okay, so if you've spent any time working with Node.js, or, really any garbage collected language, you probably know the exact uncomfortable reality we're tackling today: production memory investigations. There's this very specific kind of dread that sets in when you realize your app is quietly just hoarding memory. And no matter how many times you bounce the service, the problem inevitably comes right back. Well, in this explainer, we're going to decode the complex web of memory retention. We're going to completely rewire how you think about heap snapshots, memory leaks, and application performance. Let's dive in. Picture this. You've got a Node.js service that's been perfectly stable for months. But suddenly, maybe after just a tiny deployment, it starts eating up just a little more memory every single day. The CPU graphs? Completely normal. Response times? Totally fine. No errors. But that resident set size, the RSS, just keeps relentlessly climbing. So your team does what pretty much every team does, right? You bump up the container memory limits just to buy yourself some time. But a week later, it climbs again, threatening to take the whole service down. Finally, someone throws their hands up, yells memory leak, and grabs a heap snapshot. But instead of that smoking gun you were desperately hoping for, you just get this sprawling, confusing mess of data. Which leaves us with a really profound question. Why do heap snapshots so often create way more uncertainty than clarity?
Well, the immediate aftermath of opening that snapshot is usually just pure chaos. You'll literally have 3 different engineers look at the exact same data and come up with 3 totally different conclusions. One person points straight at a massive cache object. Another blames this humongous array that just seems to be everywhere. And the third engineer sees thousands of request-related objects and immediately assumes network requests are just never getting cleaned up. And nobody agrees. Why? Because they're all getting distracted by false suspects. They see these massive, highly visible objects and just assume they've caught the bad guys. But in reality, those giant objects are almost always innocent victims. They're just symptoms of the actual problem, not the root cause.
To make sense of this, we need to completely bust a massive myth right here, right now. Snapshots do not show memory leaks. I know it sounds crazy, but a heap snapshot only shows what memory is currently retained at that exact, precise millisecond in time. And retained memory is not automatically leaked memory. Think about it. If you have a cache that's intentionally holding on to active user session data, that's retained memory literally just doing its job. An active request holding onto incoming file buffers, retained memory. A background queue waiting to process 1,000 emails, still retained. The snapshot cannot magically tell you if an object should still exist. It only tells you that it does exist.
And realizing that limitation is a massive game changer. It totally shifts how expert debuggers approach these tools. See, the old way of thinking treats a snapshot like a metal detector. Sweeping back and forth, hoping to hear a beep and find a hidden leak. But the expert way? They don't use snapshots to find leaks at all. They use them to understand memory ownership. That one tiny distinction changes absolutely everything. You stop being a treasure hunter digging around for large objects, and you become a detective tracing lines of accountability.
Because at the end of the day, memory leaks are fundamentally ownership problems. Instead of asking, hey, which object is large and taking up space, the question you actually need to be asking is, who is keeping this object alive? An object only survives in memory for one reason, because something else is still holding a reference to it. It has a protector. And honestly, until you figure out that specific chain of ownership, staring at all those raw numbers in a snapshot is basically a completely meaningless exercise. So to really grasp how this ownership works under the hood, we've got to look at the mechanics of the V8 JavaScript engine. You have to stop thinking about isolated floating variables and really start thinking in graphs. Imagine this massive, intricate web where objects are nodes and the references between them are the connecting edges. The absolute golden rule of this web is reachability. If an object has an unbroken path all the way back to a root, it survives garbage collection. The garbage collector literally walks this web, starting from those roots, which are things like global variables, active timers, or pending promises, and anything it can reach, it keeps. But if that path gets severed, the object drops into the void, and V8 cleans it right up.
Now, the crucial mechanism here is the ownership chain. Let's trace a classic hostage situation together, all right? Imagine you spot a lingering request object in your snapshot. Why is it still there? Well, because a closure is referencing it. When a function is defined, it traps its surrounding state in a closure, so it has the context it needs to run later. But okay, why is that closure still alive? Because it's being held by a timer. And why hasn't the timer fired and died yet? Because a global scheduler owns it. See, the request object itself is just an innocent bystander. It's totally not the bug. The fact that a globally scoped scheduler owns the timer, that owns the closure, that traps your request, that unbroken chain of custody is your actual leak.
And this chain of custody perfectly highlights the absolutely vital difference between shallow size and retained size. Think of it exactly like a massive iceberg. The shallow size is just the tip visible above the water. It's the immediate physical space the object itself consumes. For a simple reference, it's practically nothing. But the retained size? That's the massive hidden chunk of ice lurking beneath the surface. It's the total amount of memory that would just magically disappear, melting away entirely, if that single object was deleted and its ownership chain was broken.
Understanding that hidden iceberg brings us to a frankly terrifying mathematical reality: gigabytes. Yep, because of how retained size works, you can have an object with a tiny shallow size. I'm talking something completely microscopic, like a single event listener or a tiny little map key that accidentally binds to an entire user's session history, acting as a retention anchor. And that invisible anchor can hold literal gigabytes of data hostage right beneath it. You could spend days sorting through massive arrays that are just victims, completely missing the microscopic 1 kilobyte object acting as the linchpin holding up that entire corrupted structure.
But here's the thing. Mastering this web of retention is only half the battle. A lot of investigations still hit a total brick wall because engineers are busy studying static memory, while the problem they're trying to solve is entirely dynamic. Think of a snapshot like a Polaroid picture. It gives you the static structure. It captures exactly what exists in one frozen moment. But telemetry? That's like a seismograph. It measures the dynamic tremors and accumulates context over time. So the Polaroid shows you the ownership structure, but the seismograph shows you the growth. And having this dynamic context is exactly why comparing two snapshots is just exponentially more powerful than looking at a single one. Honestly, one frozen moment tells you almost nothing about application behavior. But if you take a snapshot, let the app run for an hour under some heavy load, and then take another one, that comparison reveals the truth. The leak is almost never a single static object you can just point a finger at. The leak is the growth pattern. It's the delta, the specific accumulation of nodes and edges that popped up between those 2 points in time.
To really nail down that growth pattern, you have to gather up all your clues and pin them to the detective's corkboard. You really can't rely on the snapshot alone. You've got to correlate that data with your automated telemetry. A huge spike in garbage collection pauses, that tells you the engine is desperately struggling to clean up memory. High allocation rates show you how crazy fast you're generating new objects. And things like request volumes and cache hit rates give you the real-world business context. Automated tools are fantastic for flagging those suspicious tremors, sure, but it still deeply requires human intuition to weave those clues together and figure out exactly where the application's lifecycle boundaries are breaking down.
In fact, the absolute best memory investigations kick off way before a snapshot is even downloaded. They start by interrogating retention contracts. What's a retention contract, you ask? Well, it's basically just the implicit agreement in your code's design, like the agreement that when a user logs out, their session data is completely destroyed, or that when a background job finishes, its payload gets released. By the time an expert debugger opens up the profiling tool, the snapshot is simply evidence used to prove a breach of contract. They aren't going on some blind treasure hunt. They show up with super clear hypotheses about which specific contract has been violated.
So, who are the usual suspects in these contract breaches? Let's walk through the lineup. Maybe you've got in-memory caches that are quietly hoarding old entries just because an eviction policy was misconfigured. Or maybe background processing queues are stubbornly refusing to let go of completed job payloads. You might even have event emitters accumulating duplicate listeners on every single incoming request, or closures that are silently capturing way more global state than they actually need to function. The most expensive issues in production are rarely these massive, catastrophic overnight failures. They're usually these slow, compounding contract breaches that gradually choke the system until the operational limits finally snap.
So, the next time the pagers go off and your application's memory starts climbing, I want you to stop asking, what's consuming memory? That question is a trap. It only leads to false suspects. Instead, I want you to ask yourself, what should have died by now? Reframing your entire investigation around expected life cycles and termination points instantly cuts right through the noise. You stop staring at those giant arrays and you start looking for the ghosts, the data that has somehow outlived its intended purpose.
Because ultimately, heap snapshots are not pictures of leaks. They are pictures of survival. Memory forensics is simply the intricate process of understanding why certain objects stubbornly, against all odds, refuse to die. Keeping this massive paradigm shift in mind, how will you change your approach the next time a production memory alert wakes you up in the middle of the night?